Hello friends, welcome back to my channel, and in this video we will discuss about the topic of independence involving two events. The problem statement goes like this. We are given that the two events A and B are independent, and we are asked to prove that A and B complement are also independent. So what are we given? The solution goes like this. We are given that A and B are independent, so that implies what? Probability of A intersection B is equal to probability of A times probability of B. Now let us look at a generic Venn diagram involving two events A and B. So we have event A and we have event B, and the corresponding Venn diagram will look like this. So if you look at if you look at the event A, so it is nothing but union of two disjoint events given by A intersection B complement and A intersection B. So this whole A can be written as A intersection B union A intersection B complement. So and these two events are mutually exclusive because there is no common area between these two guys. So now if you take probability, we get probability of A would be equal to probability of A intersection B complement plus probability of A intersection B, and the third term would be equal to 0 because these two events are mutually exclusive. Okay, so what is that we have got? We have got that probability of A is equal to probability of A intersection B complement plus probability of A intersection B. But we are given that A and B are independent, and hence we can replace this probability of A intersection B with probability of A times probability of B. So what happens? We get probability of A is equal to probability of A intersection B complement plus this probability of A intersection B can be replaced with probability of A times probability of B. Now let us bring this probability of A times probability of B to the left hand side. So what we get? We get probability of A to be common, and that can be taken out, and we get finally 1 minus probability of B. But we already know that 1 minus probability of B is nothing but probability of B complement. So what do we get? We get that left hand side would be equal to probability of A times probability of B complement, which is equal to the right hand side, which is probability of A intersection B complement. So what is that you observe here? You observe that the intersection of two events A and B complement, probability of those probability of that intersection of those two events can be written as product of individual probabilities. What does this mean? This means that the two events A and B complement are independent. Why? I repeat, we were in a position to write probability of A intersection B complement as probability of A times probability of B complement, which is product of individual probabilities. If you can achieve this, then implies that the corresponding events are independent. So let us proceed to the next problem. So what is that? So it is again the statement is same. What is that? If we have two events A and B which are independent, now we have to prove that A complement and B are also independent. So previously we proved that A and B complement are independent. Now we will prove that A complement and B are also independent. So this is just the same way how we did before. So again we have the Venn diagram, generic Venn diagram involving two events A and B. Now instead of choosing A as we did before, now let us choose B. So this whole B can be again written as union of these two mutually exclusive events, which are A intersection B and A complement intersection B, and hence we write B to be equal to A complement intersection B union A intersection B. Now if you take the probabilities, what will happen? We get probability of A would be equal to probability of A complement intersection B plus probability of A intersection B, and then we replace probability of A intersection B with P of A into P of B and do the similar process what we did before. We can prove this results. I will leave it to you to prove that because it just few more steps involved. Okay, right. So next, the third and last one would be if two events A and B are independent, then A complement and B complement are also independent. Okay, so how do we prove that? So to prove this result, we will take the help of De Morgan's law, which states that A complement intersection B complement is same as A union B complement. Now if you take the probabilities, what will happen? We get probability of A complement intersection B complement is same as probability of A union B whole complement. But using the property of probability, we will get one probability of A union B whole complement is same as 1 minus probability of A union B. So let us substitute the expanded equation of probability of A union B in the result which we obtained before. So we get probability of A complement intersection B complement is equal to, we got 1 minus probability of A union B. So that probability of A union B can be replaced with this term. So you will get 1 minus of probability of A plus probability of B minus probability of A intersection B. Now the just expansion of this is same as 1 minus P of A minus P of B, and this minus times minus is plus, we'll get P of A intersection B. Now let us invoke the property of independence. So what will happen? So we can replace this probability of A intersection B with P of A times P of B, and hence what happens? We get probability of A complement intersection B complement is equal to 1 minus P of A same as this minus P of B same as this, but P of A intersection B can be replaced with P of A times P of B. Okay, now what happens? Let us put common terms together. So 1 minus P of A, let us put that in a square bracket, and in last two terms I take minus P of B common, so you get 1 minus P of A. So yes, so and then you can easily see that, and in these two terms 1 minus P of A is common, correct? So what happens? So you take 1 minus P of A out, you get 1 minus P of B. But we already know that 1 minus P of A is same as P of A complement, and 1 minus P of B is same as P of B complement. So what is that we have proved? We have proved that product probability of A complement intersection B complement is same as probability of A complement times probability of B complement. Again, what is that you observe? You observe that if the probability of intersection of two events can be written as product of individual probabilities, then those events are independent. Okay, so that's what we have proved. We have proved that A complement and B complement are also independent. Okay, so let us summarize what we have seen here. So we have seen that if two events A and B are independent, then A and B complement are also independent, A complement and B are also independent, and finally A complement and B complement are also independent. Okay, so but no question arises, so what happens when there are three or more events? So we will discuss that part in a later video. Okay, so in this video we have seen the concept of proving independence of two events A and B, and we have proved that those complements, the corresponding complements are also independent. Thank you.